We have been talking about binary representation, right? Patterns of ones and zeros stored inside of the machine that are supposed to, well, represent something, right? Could be an integer value, could be, hey, we talked about analog values, right? It could be the reading coming from an A to D converter that's connected to some sort of a sensor. So, if I've got a pattern of ones and zeros, all right, pattern of ones and zeros. What does it represent? We don't know until I tell you exactly what format or what representation is being used here for this pattern of ones and zeros. If it is unsigned binary, then it could be that this is the 128th position, this is the 16, 4, 2, 1. So it could be 128 plus 16. So that's what, 144 plus 4, 148. Plus 2, which is 150, 151, all right? It could be BCD, where this nibble represents the tens place and this one represents the ones place. So a 1 in the eighths position, a 1 in the ones position, that could be 9 for 90. And then we have these 4 bits right here. We have 4, 2, 1. Added together is 7, that would be 7 ones, 97. Completely different value. It could be the analog to digital converter's output after reading a temperature sensor, which represents anything because we don't know what the minimum is, what the maximum is. We do know what the bit depth is. The bit depth would be 8 bits. There's another thing that it could represent, and this thing would be a position. Take a look at this image. This image shows a rather crude way of measuring a position of a shaft, a rotating shaft. There are 8 positions, and what you have is 3 LEDs shining from one side of that disc with the slots in it, and where there's a slot, it allows light to flow through to the sensor, which would indicate a 1 if it sees light, a 0 if it doesn't see light. Well, let's take a look at this sequence of bits for this sensor. So I've got 3 bits. I'm just going to label them B sub 2, B sub 1, and B sub 0. The 0, 1, and 2 representing the digit position, the 2 to the whatever position. So this is the 2 to the 0 position, 2 to the 1 position, 2 to the 2 position. And if this platter or the shaft turns and that platter allows light to shine and then turn off, as you go through the sequence, you start out at 0, 0, 0, go to 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This would represent the different positions. Now, there's a problem with this, and the problem is this. As you're going through these sequences, you may have a position like, for example, let's take a look at going from that position to that position right there. Now, not all of those LEDs and sensors are going to be precisely synchronized. They're not synchronized with each other. They're just changing based on whether the sensor sees light or the sensor doesn't see light. If perhaps this bit changes just a moment before these bits change, and we happen to read at exactly that moment where bit B2 changes before bit B1 and B0 change, we're going to get a reading of 111 for just a moment, which tells us that the shaft had turned to this position really quickly, and then you don't realize until the next reading that you actually were going to this position. Is this a problem? Well, picture if this shaft just happens to be the shaft that's measuring the position of a throttle on a car. Would you happen to want it to look like the throttle suddenly got floored for just a moment and then was released? No. That's not an optimal condition. So we have another way of representing a sequence. So these bits, in this case, do not match up with powers of 2. Instead, it's just a reordering of the binary pattern of ones and zeros. And we are going to, well, one of the names it's given is gray code. And gray code is not a numeric sequence, it is a sequence of patterns, so that situations like we have with going from 0, 1, 1 to 1, 0, 0, we don't have that accidental misreading that could happen in the middle. And the way it works is we have reorganized these patterns so that only one bit changes at a time. And the pattern goes something like this. So we still start out at 0, 0, 0. And then go to 0, 0, 1. But instead of going to 0, 1, 0, where 2 bits change, we go to 0, 1, 1. We only change the center bit. Then after that, we go to 0, 1, 0 and grab that pattern that we skipped over. Now, if you look at these 4 patterns right here, when you go from pattern to pattern to pattern to pattern, only 1 bit changes. That way we can't have that erroneous intermediate read as the bits are all changing at one time. Once again, this is not a numeric sequence. It is simply a sequence to identify a pattern or position. This next pattern right here is going to be 1, 1, 0. Still only 1 bit is changing, going to the next pattern. Then we have 1, 1, 1, 1, and then we get 1, 0, 1, and then 1, 0, 0. Now something that's really important to see here, to note here, is that if this shaft continues turning, for instance, it doesn't have a stop. It doesn't stop whenever it gets to the 8th position. It wraps around and goes back to the original position. Look, the bottom line here, 1, 0, 0. If we come back to 0, 0, 0, still only 1 bit changes. Well, that seems to be nice. All we've done is we have reordered our sequence of bits so that there's no 2 bits changing at any one time. Only 1 bit at a time changes. Well, how do we make one of these sequences? This sequence was pretty easy with making only 3 bits. In fact, it's pretty easy to make it just with 2 bits. But how do we make a sequence for, say, 6 bits or 8 bits? Is this a position, or what exactly position does that reflect? Well, let's talk about the real simple way to generate one of these sequences. First of all, if we have the sequence 0, 1, that is just the sequence for a single bit. Now we don't have to worry about that. Naturally, that is gray code, because if we go 0, 1, 0, 1, 0, 1, there's only 1 bit to change. There's only 1 bit that's going to change. Now, how do we make a 2-bit sequence? The way we make a 2-bit sequence is we reverse the order of what we had before. So I had 0, 1, now I'm making 1, 0. I'm going to add another bit here. I'm going to start with the first 2 patterns being 1, and then for the patterns that got reversed, first 2 patterns I'm going to start with 0. So I have 0, 0, 0, 1. And then where I reversed the pattern, I'm going to precede that with 1s. Let's try this again. I'm going to take the single bit pattern. I'm going to make a copy of it in reverse order below it. I'm going to, for the original pattern, precede it with 0s. For the new reversed order, I'm going to precede it with 1s. There's the gray code. And in fact, if you see here, I've got this gray code in these first 4 rows for just the last 2 bits. Let's try this again, because maybe that wasn't clear. I'm going to take this pattern and I'm going to write it in reverse order. 1, 0, 1, 1, 0, 1, 0, 0. Now, where we had the original sequence, I'm going to add a 3rd bit of all 0s. It's going to precede those 2-bit patterns. Then, where I reversed the order, I'm going to add a preceding 1. And now we have our 8 position or 3-bit pattern. How about going to 4 bits? Well, to go to 4 bits, what we need to do is reverse this pattern. So we're going to go 1, 0, 0, 1, 0, 1, then 1, 1, 1. Then the next one is 1, 1, 0. Then we have 0, 1, 0, then 0, 1, 1, then 0, 0, 1, and lastly 0, 0, 0. Now for the top half, we're going to precede with our 4th bit of all zeros. For our bottom half, we're going to precede with our 4th bit of all ones. And there's the 4-bit pattern. Now, this can be a bit tedious. So, let's look at this in another way. If I numbered simply each one of these sequences as giving them an order number, this would be 0. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, each one of those patterns has a corresponding unsigned binary value. Let's, for example, pick 12. If we come down here, so this was 15, 14, 13, 12, so this is the 12th position. 12 in unsigned binary is 1, 1, 0, 0. So that is 12. Remember, we've got, this is the 8th position, this is the 4 position, 8 plus 4, that's 12, and that gives us this 12th position. Now, is there a way to go from this number to this pattern? Turns out there is. Let's just start with the 1, 1, 0, 0. Now the process goes something like this. Precede this pattern, this number here, with the number 0. All right, so all we're doing is we're adding a 0, we're appending a 0 to the beginning of this. Now what we have is 1, 2, 3, 4 pairs of numbers. If the numbers are different, as in these first 2 values, if they're different, put a 1. If they're the same as in this next pair, where this one's a 1 and this one's a 1, if they're same, it's a 0. Once again, we have the next 2 bits, 1, 0, those are different, there's a 1. These next 2 bits, they are the same. 0 is the same as 0. Same, put a 0. So when they're different, put a 1. When they're the same, put a 0. All right? Notice that this pattern here, 1, 0, 1, 0, is the pattern we got to after doing our sequence. Works exactly the same way, except in this case, all we have to do is just simply come up with the sequence value from the sequence number. Okay? Let's try this with more bits. Let's try this with more bits. Let's do a 6-bit position number. I don't know, we'll make something up. 1, 0, 1, 1, 1. Okay? That's we'll put a preceding 0 here, okay? So there's a 6-bit value, all right? In fact, let's do the next one in the sequence too. If we add 1 to this guy, we get 0, 1, 1, 0, 0, 0. So if this is the number, the position within the sequence, the binary number that represents that position in the sequence, notice if we go from here to here, 4 bits change. All right? Let's see what the gray code looks like. Remember, it's a 2-step process. Start out by putting a 0 at the beginning of this number. If they're the same, our gray code is going to have a 0 in that position. If they're different, our gray code is going to have a 1. Different, 1, different, 1, same, 0, same, 0. So, what is this value? This value right here is, what is this? 16 plus 4 is 20, plus 2 plus 1 is 23. So that number right there is 23 in decimal. So the 23rd position, assuming that the first position is the 0th position. So the 23rd position, and let's double check and make sure we've got that right. 16 plus 7 is 23. So the 23rd position in gray code sequence is this right here. What does the 24th position look like? Well, put a 0 there. Same, 0, different, 1. Same, 0, different, 1. Same, 0, same, 0. So this is the 23rd position. This right here is the 24th position. How many bits does this differ by? Turns out this bit right here, that bit position right there, is the only one that changes. So, not only can we generate a sequence just simply by doing that mirroring and then preceding zeros and preceding ones, but we can also generate the sequence using this algorithm where you precede with a 0 and then do the difference and the sames. Great code. What's the reason for great code? It's we're going through a sequence and we only want one bit to change at a time in order to prevent any sort of errors.